Hello all. In this video, I'm going to brief you regarding the second order reaction. Particularly, how do we arrive at the integrated rate expression for a second order reaction. Now you're familiar with what is the order of a reaction. It is nothing but the sum of the powers of the concentration terms of the reactants in the experimentally determined rate equation for the reaction. And hence, for a second order reaction, the sum of the powers of the terms will be equal to 2. Let us take up few examples. Let us see one or two examples. Now here you have the formation of HI. Here the rate expression is given as rate equal to K into H2 into I2. The sum of the powers of these two will be equal to 2. Okay. Another example, here you have reaction between NO2 and fluorine. Here, even though there are 3 molecules of reactants involved, in the rate expression only 2 molecules appear, and the sum of their powers is equal to 2. Another case, here we have HI, only one molecule, that is in decomposition of HI, only one reactant is involved, but in the rate expression we are raising its concentration term to 2. So the order of the reaction will be 2. Okay, so basically we can say that there are 2 types of second order reaction, isn't it? That is, wherein there are 2 different reactants, or when there is only a single reactant. Okay, so basically we can classify or put second order reactions. In order to derive the integrated rate expression, we can take up 2 cases for second order reaction. In the first case, there is only one reactant, or when there are 2 reactants and both the reactants are having the same initial concentrations. So these 2 cases we are putting into one to derive the integrated rate expression. Okay. So when there is only one reactant, that means the decomposition of HI which we had taken earlier, or when there are 2 reactants, that is, you can take up an example of formation of HI. There are 2 reactants, hydrogen and iodine, but both these reactants are having the same initial concentration. So these 2 cases can be put as case 1 to derive the expression, and case 2 when there are 2 reactants, but these 2 reactants are having different initial concentrations. Okay, so in this video we'll be dealing with the first case, that is either only one reactant present or 2 reactants present with the same initial concentration. Okay, so let us take up that case, and let us write the general expression for, equation for these 2 cases. That is, one reactant present, its rate expression, the concentration term will be raised to 2. There are 2 reactants present, and rate expression, you will have both these 2 reactants appearing in the rate expression, and the sum of the powers of this concentration terms will be equal to 2. And remember here, A and B will be having the same initial concentration, isn't it? So you can take the initial concentration of A and B be A moles per liter, and after time t, X moles of A or B would have got reacted. So that X will be the decrease in concentration of A or B after time t. And so after time t, the concentration of A or B remaining will be A minus X moles per liter. So here, if you in this assumption, we are taking the concentration of A and B as the same. The decrease in concentration of A and B will be the same. Okay, and the initial concentration of A and B will be the same. So if you put this here, in both the cases it will be, if you are considering initial, you will get A square here, and in the second case, concentration of A will be A and also B will be A, so put it together, you get A square. So in both these cases, the integrated rate expression will be the same. Okay. Now, since we have taken these assumptions, we can come up with the rate expression in terms of the instantaneous rate expression. In terms of decrease in reactant rate will be equal to minus d into my A by X by dt, or in terms of formation of product, rate equal to dx by dt. And then we have the rate expression, rate equal to K into A minus X the whole square. Okay, you can compare equation 1 and 2, because in both the cases it is a rate which is being determined. So you can compare these 2 and you can come up with dx by dt equal to K into A minus X the whole power 2. That will be equation 3. Alright, rearranging that, putting all the x terms together, you get dx by a minus x the whole power 2 equal to k dt. Now you can integrate equation 4. When you integrate equation 4, you get equation 6, that is 1 by a minus x equal to kt plus c, where c is the constant of integration. Alright, so after integration you get 1 by a minus x equal to kt plus c. Okay, now with this equation, you have the equation 6. We know that at time t equal to 0, when time t is equal to 0, that is initially x will be 0, isn't it? Initially x will be 0. And so this equation 6 will become 1 by a equal to c. Now you can put equation 7 in equation 6, that is instead of c you can put 1 by a, then you get equation 8, that is 1 by a minus x equal to kt plus 1 by a. Okay, rearranging this equation 8, you arrive at kt equal to 1 by a minus x minus 1 by a. Again rearranging, you get k equal to 1 by t into 1 by a minus x minus 1 by a. And we know that a minus x is the concentration of the reactant at time t. So it can be put as Ct, and a can be put as C0, that is the concentration of reactant at time 0. Okay, so you can rewrite equation 10 as k equal to 1 by t into 1 by Ct minus 1 by C0. Okay, so these two, either equation 10 or equation 11, is called the integrated rate expression or rate equation for a second order reaction. Okay, equation 10 or equation 11 can be considered as the integrated rate expression for second order reaction. And when you see that, you can see that if you want to know the unit of the rate constant, we have the concentration terms and the time term in the denominator, and so the unit of K will be equal to liter mole inverse per second or liter mole inverse second inverse. That will be the unit of K. Alright, so this is the integrated rate expression, and liter mole inverse second inverse is the unit of K for a second order reaction. Alright, now let us see what will be the expression for fractional change or for the T half of a second order reaction. Alright, that is the half-life period. Now you are familiar with half-life period or T half. It is nothing but the time taken for the completion of half of the reaction, isn't it? Or time taken for conversion of 50% of the reactant to the product. And we have the expression, integrated rate expression, K equal to 1 by T into 1 by Ct minus 1 by C0. Alright, so that is here, when T is equal to T half, you can put Ct will be equal to C0 by C0 by 2, because after T half, 50% of the initial concentration of the reactant would have got consumed. Okay, so you can put when T equal to T half, Ct equal to C0 by 2, therefore K will be equal to 1 by T half into 1 by A by 2 minus 1 by A, where A is the initial concentration of the reactant. Now simplifying this term, you get T half equal to 1 by Ka. Now from this expression, you can see that the half-life period of the second order reaction is inversely proportional to the initial concentration. Remember, for first order reaction, the half-life period was independent of the initial concentration of the reactant, but here the half-life period for a second order reaction is inversely proportional to the initial concentration. Now same is the case for any fractional change, be it T3 by 4, T1 by 4, okay, so for any fractional change, the time is inversely proportional to the initial concentration of the reactant. Okay, so you have to remember this equation for second order reaction. T half is equal to 1 by Ka, where K is the rate constant. Now, how do we, how will the graph of this second order reaction appear? Let us see. You have the x-axis and you have the y-axis. In x-axis we take up time t, and in y-axis we take up 1 by a minus x or 1 by ct. Okay, and when you plot a graph of 1 by ct versus time t, you get a straight line with an intercept. Alright, now the slope of the straight line will give you the value for k, okay, and the intercept will give you the reciprocal of the initial concentration, that is 1 by a. You will get the value for 1 by a. So when you plot a graph, you can arrive at k and also at the initial concentration of a. That's important. I mean, initial concentration of the reactant. So what is the reactant present initially can be easily predicted from the plot of second order reaction. When you plot 1 by a minus x or 1 by ct, concentration at time t versus time, you get an intercept, and that will give you the value for the initial concentration. Okay, so this is the plot for a second order reaction, plot of 1 by a minus x or 1 by ct against time t for a second order reaction. Right? So hope this much is clear to you regarding the second order reaction. If you have any more clarifications to be done, please feel free to ask me. Thank you.